All right, 10.1, the beginning of a fun and exciting chapter, in my opinion. Uh, so let's use this example. Let's say one day you get graduated, and it is time for you to go off to college. And a lot of kids going off to college, young adults going off to college, will be blessed with a computer. Their parents might buy them, or maybe they got enough graduation money they decide that's what they're going to spend their money on. So, pretty common deal. Um, so let's say you've decided to get a 15-inch MacBook Pro. Pretty nice. Um, Now we know there's a lot more options in this. Let's just say that the only two options are which processor you get. That's it, 2.6 or 2.7, and those are all the options you have. Of course, we know that that's not the case. There are more choices than that, and we'll deal with that in a second. But the question is, how many different MacBook Pros could you make? Assuming you pick the 15-inch. Well, right now there's just two. Right, so we're making a MacBook Pro. So we have one of two choices here. We have two processors, the 2.6 and the 2.7. And, this is a processor. It's got its little pins coming off. So if these are the only two choices, you could make two different MacBook Pros. One of them is 2.6, one of them is 2.7. Of course, there's more options than that. We can go on from there to the kind of hard drive we want, whether it be a standard hard drive that has moving parts or the static state, or the solid state that doesn't have any moving parts, like a flash drive, right? So we could choose the 2.6, and then we could choose this, or this. You have 6 choices there, right? All right, let's go over here to our diagram here. So we could choose any of those 6 hard drives, right? But we could change our minds. We could instead do a 2.7, and we could run through these 6 choices again. Okay. So we have the same 6 choices if we go with the 2.7, and that is 5. Okay. So now we don't have just 2 choices. We have this choice that has 6 offshoots, and this second choice that has also 6. So altogether we have 12. We have 12 choices, 12 different MacBook Pros that we could make. Okay. Well, let's keep going. There's more choices than that. We now choose a display. Could be glossy, could be high-res and glossy, could be high-res and anti-glare. So now at the end of our choice for a processor and then a hard drive, we now have 3 choices for what kind of screen to get. So we've got 3 choices here off of the end of each of these. Okay, so we're getting lots of choices here. And in the end, what we want to do is count all those choices at the end, how many completely unique MacBook Pros can we make. So here, our next choice is whether or not we want to be able to hook up to this external display. It's a really nice, big, huge screen. Do we want to be able to hook up to it, or don't we? We don't, or we do. Okay. So after we choose our 2.6, what was it? Gigahertz. Yes, of course. We choose our 2.6 gigahertz and our whatever size moving parts hard drive, and then we choose the 15-inch glossy display. Now we choose either we do want to hook up to the Thunderbolt or we don't. So that's what each of these little 2 branches is about. These are called branches because it's called a tree diagram, because it kind of looks like a tree, maybe a tree that fell down sideways. Okay. So the end of each of these little branches at the very end on the right here represents a unique MacBook Pro that we've put together. Okay. And There is another choice. You could pick your keyboard. That's really a choice of language. So let's assume that we choose the English language. I think most of the people watching this, since I'm talking in English, are going to choose English. So the question is, how many unique MacBook Pros can you make? And to use just the tree diagram to count each of these little things here, it would take a long time. But it doesn't take long to figure out how to count them more quickly, right? First, we have 2 choices for processors. Then after that, we go on to make one of 6 choices for our hard drive. And then we go on to make one of 3 choices for our screen display. And then we go on to make one of 2 choices whether or not we want to hook up to the Thunderbolt. So, how do we count all of these possibilities? We've got 2 groups of 6 choices, right? 2 groups of 6. That is, if you haven't heard that as a definition of multiplication, I don't know where you've been. But 2 groups of 6. We have 6 here and 6 here, and that by definition is multiplication. Okay, so we have 12. So we have 12 branches now. Each of those 12 branches has 3 more coming off of it, so we got 12 groups of 3, so we just multiply that by 3. And each of those branches, however many that turns out to be, has 2 choices coming off of it, so we multiply that by 2. Okay, then we get out the old calculator, and I've done this one time before. 2 times 6 times 3 times 2. Actually, we did times 4, because it's so easy. Let's just say maybe we want Japanese on our keyboard. So we'll give it 4 more choices. So 288 possible MacBook Pros that you could put together. Okay, so this is called the fundamental counting principle. And you may have seen it before. You know to multiply each of those things together. So the fundamental counting principle just says if there's some event, like the event that you choose a processor, and it can happen m ways, and there's some event after that, like choosing a hard drive, and that can happen n ways, and a third event that can happen p ways, and any number of events, like the last event can happen z ways. Then we just do m times n times p times however many different choices we have, all the way down to this can happen z ways, just like we did here. 2 ways times 6 times 3 times 2 times 4 ways, and gives 288 possible combinations that we could put together. So the fundamental counting principle, fundamental meaning a lot of things are going to be built off of it. Okay. Now let's say that it's your day of departure. You're leaving for college. And let's say you're leaving for college with 3 of your friends. They just happen to be going to the same school. So the choice you have to make now, before you physically get in the car and leave, assuming let's say you have a 4-passenger car, how many different ways can you get into the car and drive away? Somebody has to sit in the driver's seat, somebody shotgun, and then 2 people in the back, right? So let's make decisions in a row. Doesn't matter what order we make them. We could choose who sits in the back first or who sits shotgun third. It doesn't really matter. But usually someone will decide to drive. Someone will call shotgun. Then you'll choose somebody sits in the back left, somebody sits in the back right. Okay. So we'll just make them in order. And it doesn't matter the order. Just like it doesn't matter the order up here. We could have chosen the hard drive first, then the processor. We could have chosen the screen, and then the keyboard, and then the hard drive. It doesn't matter. Right? So we just choose an order and realize that we could have done this in any order, and it would all be the same answer. So how many drivers do we have? Well, nobody has said that they want to do anything yet, so any of the 4 people could jump in there. After that, somebody calls shotgun, right? So that's 3 possibilities for shotgun. because somebody's already driving. So that person's not going to be able to sit in the passenger front seat. After that, two people, the driver and the shotgun person here, the co-pilot, have been chosen. So there's only two people to sit back here. So one of those two people is going to choose to sit in the back left, and the last guy is just going to sit in the last seat that's available. So 4 times 3 times 2 times 1, 12. 12 possibilities for you guys to jump in there and arrange yourselves and drive away, right? And anytime that you want to arrange a certain number of things, a set number of things, it's going to be exactly like that, right? What if you're going to college and it's not just a sedan that you're going to drive? You're going to drive a minivan there. So let's see, you could fit 1, 2, 3, 4, 5, 6, 7 people in a minivan. Maybe 8. So let's say 7, right? So now we're in a minivan. All 7 of you are going to go. Well, one of the 7 people is going to drive, and then one of the 6 people that are left are going to sit shotgun, and then one of the 5 remaining people is going to sit behind the driver, and one of the 4 people is going to sit behind the shotgun, and then one of the 3 is going to sit in the back left, one of the last 2 is going to sit in the back middle, and the last person is going to sit in the back right. Right? And we would just multiply all of these together. What am I doing here? This is what I want right here. Okay, so then we do 7 times 6 times 5 times 4 times 3 times 2 times 1. Enter. 5,040. That's a lot of combinations. 5,040 possible ways to arrange yourselves in a minivan. When we start to look at just slightly bigger numbers, right, that we want to arrange in a certain order, the rate at which they grow is pretty amazing to me. Anyway, I'm wasting time. Well, now let's say you're going to take a bus. All right, there's so many of you going that you're going to take a bus, and let's just say we assume that a qualified bus driver is going to drive. But let's say that there are, how many people can you fit on a bus? I don't know, 50. There's got to be more than that, but let's say 50, because that's just daunting enough, right? Somebody's going to sit right behind the driver, and then somebody's going to sit right next to that person in those big love seat style seats that are on a bus. So one of the 50 people is going to sit right in that spot, okay, and then the person is going to sit right next to them, any of the remaining 49, and then across the aisle, one of the 48 remaining people, and then the next guy that's across the aisle but sitting by the window, there's 47 people left. You see where I'm going with this, all the way down to, we get all the way down to the back of the bus until we have, say, in the very back row, 4 people left, times 3 people after that, times 2, times the last guy sitting in the very back next to the window, if we make our decision in that order, which is a fine way to make it. So, wow. I don't really want to sit here and multiply 50 times 49 times 48 times 47. So here's the good news. There's this notation that we use as a shortcut, because we want to do this so often that we've standardized it with a symbol. Our calculators know this symbol. Other mathematicians know this symbol. If we want to multiply 50 things together like this, from 50 all the way down to 1, that's 50. That's not 50, emphatic 50. That exclamation mark is a symbol that stands for the word factorial. So this guy says factorial. And factorial means multiply this number by every number that comes before it. So, how do we do that? We got 50, and I don't want to do times 49 times 48, and so on and so on. We want to go into math, over to PRB meaning probability. We're getting into probability. And factorial right there. We got the exclamation mark. I don't even know if it's going to be able to do this. It does. Okay, it does it. 3.0414 E64. Remember that E see, let's do to 3.0414. So 3.0414, and that e means times 10 to the whatever power we saw. What was that power? 64. My goodness. So what does that mean? This number, to actually get a feel for how big it really is, we take this decimal place and move it 64 times to the right. And once we're done doing all that, that is the number of ways that you could arrange yourselves on a bus if there's 50 of you going. Goodness gracious, that's a lot. Okay. And there's a slight variation on this. If we want to arrange so many things, but some of those things are identical, okay, so let's say we just have repeated items, and you can't really do this to people because people are unique snowflakes and everybody's wonderful and different, so you can't say that they're repeated items. So let's use the example of a pretty simple word like tennis. Right? So you got this word tennis, and let's just say, for the heck of it, we just want to see how many ways can we arrange these letters. Right? For one example, S-I-T-N, what do I have left here? N-E-N. Okay? Sitten. Not really a word, but we'll just call it by definition a word. It's just a unique arrangement of these letters. Okay? And you might say, well, hey, we've got 6 things. We just learned this. We got 6 things, and we want to arrange them as many ways as we can. So why don't we just do 6 factorial? And I would say that that's a good idea, because that's exactly what we just learned, except for if we count it using 6 factorial. Now I'm going to talk about 6 factorial like it was a brain or a computer or something that thinks. Okay, 6 factorial thinks that that n and n are different. Just think about it. 6 factorial would be the way that if there were 6 people riding in a car, each of them unique as a snowflake, you would use 6 factorial to count how many ways there are for 6 of them to get into a car or to stay in a line or whatever. So 6 factorial treats each of these like a unique snowflake, except for n and n are exactly the same thing. But when you look through 6 factorial's eyes, it sees, just helping you see what 6 factorial sees, it sees n, like this n, as a different one. So it sees it as like bright green n and blue n, but there is no difference between those two. Okay? So what 6 factorial would do here in this example is, let's say that it says, I'll put the blue one first and then the green one second. And then I will rearrange it into a unique arrangement like this and put the blue one second. But we look, and sitten are the same word. So that doesn't work. Not quite. 6 factorial doesn't quite work. Okay? So think to yourself, how many ways does 6 factorial count each of these words? If I wrote a different word here, well, let's just take like tennis, for example. It would do this, and then it would write the blue N, and then write the green one, right? And that's 2 different words that it can make. And if we tried to make up another word, okay, so it would say put the blue one second, and then it would put the blue one first. So how many different ways does it count each of these words? It counts them 2 different ways. It counts this one 2 different ways, however many ways it can arrange those 2 n's, 2 ways, 2 ways. It overcounts, right? It counts too much. It overcounts by twice as much, right? So what we would need to do is take 6 factorial and divide it by 2, because there's just twice as many words as we need, so we'll just divide it by 2. Let's think of another word. How about pepper? The word pepper. I don't want 2 e's. Here, let's go with popping. Popping. Okay, the only repeating letter is P, but there's 3 of them this time. Okay, so, and we'll go over this a little bit again in each of the problems in the next video, but we'll start with our however many letters there are factorial, right? So there's 1, 2, 3, 4, 5, 6, 7. So we'll go with 7 factorial, right? But 7 factorial, if it's a thinking thing, it thinks that P, this P, that's a terrible color to use. It thinks that this P and this P and this P are 3 different P's. So every time it gets a hold of a word like P-O, P-P-I-N-G, it will take all 3 of those P's and rearrange them however many different ways that they can be arranged. Right? This is the simplest way to think about it. So it counts each word that many times. However many ways it can arrange those 3 P's, it counts it that many times. It overcounts it that many times. So we say, let's get black first, and then let's divide this down so that it's the appropriate number, right? So it's overcounting by 3 factorial, right? There's 3 factorial too many words. So you're going to divide it by 3 factorial because for every word that it gets a hold of, it arranges those P's as many ways as possible. And how many ways can you arrange 3 things? Well, that's just back to here, back to the factorial. There's 3 factorial ways to arrange those 3 P's. Okay, now let's take one last example. Let's go with the pepper example. Let's say pepper. Okay, now we've got an interesting situation here because we've got 3 repeated P's and 2 repeated E's. Okay, so we've got 6 letters here. We'll start with 6 factorial, and then we're just going to fix it. Right? 6 factorial just counts it too much, and we're just going to fix that. Right? So for the P's, we've got, for every word that 6 factorial makes with pepper, it's going to arrange those 3 P's in 3 factorial ways. So we're going to divide that by 3 factorial. All right. It's also going to arrange the 2 E's in as many ways as 2 E's can be arranged, which is 2 factorial ways. So we divide it by 3 factorial times 2 factorial, and that gets us down to the actual number of unique arrangements of these letters that we can possibly have. So we've looked all together. Let's just scroll down. I'm talking about just these last 2 examples. Here we've looked at if you want to arrange n things, right? And let's come down here. We have a little more room. If you want to arrange n things, that's n factorial. If you want to arrange n things with r repeated items, much better. We do n factorial over r factorial. Or if you have also q and s and so on, you r times r factorial times q factorial times s factorial. And we just keep doing this for every repeated item that we have, right? In the example pepper, we had 3 repeated P's and 2 repeated E's, and we would keep going if we had any other repeated items. All right. So the last thing is, if we now want to go back to having just a set of things, and they're all going to be different in this one. So let's say we have what color to use. Let's say we have n unique things, and we want to arrange r of them. How would we do that? So let's say that let's take the minivan situation. There's 7 of you, but you don't have a minivan. You only have 2 cars, right? So 4 of you are going to go in one car, 3 in the other. So how do we choose who's going to jump in the first car with 4 people? We just want to know how many ways are there to put 4 unique people in a unique arrangement into the first car, right? How does that happen? Well, it's any of the 7 people, right? Because there's 7 people that are going to hop in a minivan, except for we only have 2 cars, so we got to split it down the middle. So any of the 7 people could jump in the driver's seat, and then 6 remaining people could ride shotgun. Then 5 remaining people could ride in the back left, and then 4 remaining people could ride in the back right. And then we stop. There's no room for the other 3 people, but there's more people to choose from than just the 4, 3, 2, 1, right? You got 7 people could ride here, 6, 5, and then 4, and then you have the other 3 people. They just need to arrange themselves in the other car. So that's how we count it. And so 7 times 6 times 5 times 4. Let's throw that in here. $840. Right? Well, let's look at this slightly differently. Let's say we started with this minivan situation here, and we just kind of got rid of the last little bit that was the last 3 people. Right? Because this is exactly the same. It's just the first part of the minivan situation. So what we could do, let's say we started with 7 factorial for this. 7 factorial. But we see now that we want to only go down to number 4 here. The 4 remaining people are going to sit in the last seat in this car, and then just take off those last 3. How can you take off the last 3? Well, you could just divide it by, right, this would be 7 times 6 times 5 times 4 times 3 times 2 times 1. But you want to divide out. Let's use division to get rid of these 3. So we'll divide out a factor of 3 and 2 and 1. Well, what's 3 times 2 times 1? That's just 3 factorial, right? So what if there were 50 of you, but you only had a fleet of cars, not a bus to take? So how many ways can you arrange 4 out of the 50 people to jump into the first car? You just take 50 times 49 times 48 times 47, right? Which is the beginning of 50 factorial. So this would be the same as if we just took 50 factorial and divided off the rest that we don't want. So we'll divide it by 46 factorial. 50 factorial divided by 46 factorial. And that would give us the 50 times 49 times 48 times 47. Let's just prove it to ourselves. Let's move this over here. Okay. So let's do 50 times 49 times 48 times 47. Okay, that's the number we get. Let's do it the other way. Let's do 50, and we'll go over here and get our factorial. And we'll divide that by 46 factorial. Exactly the same thing, right? So let's hide this. For this, there's a shortcut. I'll talk about the shortcut in the sample videos, just to keep down the length of this video, which is already tremendous. Thanks for hanging in there. I know there's a lot of stuff crammed into this section. You hung in there for the intro, and now we'll do some sample problems. Thanks for watching.